All right, good afternoon, everyone. I'm David Arate. I'll be presenting with Karandev Singh here. So this is an update on the Merced River Watershed FloodMAR Reconnaissance study. We've been working on this study for quite a while now. I think about a year or so ago, I had given a presentation to the LunchMAR group on the model integration. We'll focus on that again a little bit, but this study will go into a lot more of the results and kind of the what we're seeing, at least as preliminary results of what we're seeing from our study through a couple of the scenarios that we've been modeling. Um, there we go. Okay. So just a quick outline for this presentation. I'll just go over the quick kind of purpose and goals of this study, a little bit of background, and then I'll present on the model integration. There's a lot of different models that we're using in the study. Kind of give a quick overview of what they are and how they integrate. And then Karandev will go into the results and discussion, and then we'll have a little Q&A at the end. Oops. Okay, there we go. So the purpose and goals of the study, kind of the main purpose of the study is a proof of concept study. A lot of you probably know a lot about FloodMAR, but with this study, we're really looking at scaling FloodMAR up to that watershed scale. Feasibility of FloodMAR, implemented at a watershed scale with a major river, major conveyance network, major reservoir, and just trying to see, does FloodMAR work at that watershed scale? Do we get big benefits? Can we prove this concept? On that topic, there's a lot of work that's gone into the modeling, a lot of work going into the results. We've gotten some feedback about, how accurate are you on these model results or in the modeling, uncertainty, that kind of stuff. That's not the purpose of this study. I just want to kind of get that disclaimer up ahead. It's really just trying to show, what can FloodMAR do? We've made a lot of assumptions with our models. We understand that they're probably not perfect or super efficient, but it's a learning process of being able to do FloodMAR at the watershed level and seeing, what can it do as we implement, greater and greater levels of FloodMAR and also with climate change. So that's really kind of the point of this study, is this proof of concept. One of the goals is this integrated watershed modeling that I'll go over. We're looking at FloodMAR at the watershed level, all different sectors. You can see here the flood risk, ecosystem, water supply. Those are kind of three main sectors, and they're really overlapping and integrating. So this watershed modeling, this integrated watershed modeling really goes into that. We're going to evaluate those multi-sector effects. Karandev will talk a little bit more about that as he starts to present some of the results. I mentioned climate change. We're going to be assessing the vulnerability of this watershed to climate change and looking at the adaptation potential of FloodMAR. And then lastly, a major goal for this study is that we hope it'll be a template for future studies and projects. We're hoping that we can get through a lot of that initial phase of investigation and R&D and modeling so that others can use this to be more efficient, to be better, to do more when they go to do their own studies or projects, such as maybe pilot projects. Okay. So just a little bit of background. So we're looking at the Merced watershed. Is a critically overdrafted basin. I think historically the overdraft is about 50,000 acre feet on average per year. There's one major reservoir in this watershed, the Lake McClure near Exchequer Dam, and then there's a few smaller kind of flood control reservoirs on some of the creeks. There's a Merced Irrigation District, controls the reservoir, controls the irrigation district here. So it's about 825 miles of conveyance through this area and about 150,000 acres of agricultural land. I just want to talk a little bit about climate change. A large part of this study is looking at climate change. We've been really working on how to incorporate climate change into the study, and we've decided to go with the decision scaling approach that the DWR climate change group has been working on. They've put out a few studies and papers using this approach, and we've incorporated in this study. The basics of this is we're using 100 years of continuous hydrology from what year 1900 to 1999. Instead of just picking a couple of future scenarios, we've decided to try to model all the future scenarios that encompass what the GCMs show as kind of the probable futures as far as changes in temperature and changes in precipitation. So here, each of these dots is a change in either precipitation, so going from negative 20% to plus 30%, that's mean annual change in precipitation, or a change in temperature from 0 degrees to 4 degrees. So each of these dots on this kind of grid is a combination of a perturbation in temperature and precipitation. And it's 100 years of this hydrology at each of these perturbations here. So some of the things that we can do with this is what we call these system response curves, is how does the system respond to all these climate change scenarios, kind of being able to visualize this all at once. So this one example, we're looking at average runoff into the Merced Basin during what we kind of consider the flood period, November 1st to March 31st. So our baseline average, which would be here at this kind of current climate, 0% change in precipitation, 0 degrees change in temperature. Baseline average is about 434,000 acre feet of runoff into the Merced Basin. But how does that change with the different changes in temperature and precipitation? So if we break these down first, just look at just change in precipitation. As you have more precipitation, you get into the blue area, which is more change, more positive change in volume runoff, and then if you get into less precipitation, less runoff. That one's pretty straightforward. With changes in temperature, though, you also see as temperature does start to increase, you get more runoff in this time period, more snow melt melting earlier, or more precipitation that comes down as rain instead of as snow, ends up with more runoff in this period. So as you combine the two, changes in temperature and changes of precipitation, you can see now for this metric, how does the system respond to climate change? And then another piece that's not on here is that we can overlay the probabilities of those global climate models and try to figure out, what does a probable future look like, to get a sense of what the probability of where we would be, in say 2040 or 2070 on this grid. But here we can see as temperature increases, precip increases, we have a lot more runoff that would happen during this flood period. Okay, so I'll move on to the model integration. This is our flow chart for how all the models that we are using for this study and how they all integrate. I'm sure this is quite confusing. We have 9 different models that we're using in our study. And I'm sorry. And there's information moving back and forth between all of these models, and there's loops in all these models, and this is really confusing to look at. So I'm going to break this down into kind of a more spatial way and step through each of these models. So we'll start by looking at our study area. We have the Merced study area here around with this orange outline. The city of Merced is here, city of Fresno out here, Stockton right here. And we've zoomed out a little bit from our study area because even though we are focusing on the Merced Basin, we do need to go out beyond for a couple of reasons. The first one is for our groundwater modeling. What happens in our Merced subbasin isn't isolated, even though this is the watershed we're looking at. What happens here is affected by the neighboring subbasins, and what happens in the neighboring subbasins is affected by what we do in the Merced subbasin. So we've had to go out beyond our study area for the groundwater model. I'm going to name a few names of who's working on all these different models, because we do have a very large comprehensive group working on all these. So for the groundwater modeling, it's Woodard and Curran that is doing the groundwater modeling for us. So then from our groundwater modeling, we can go to our system operations model. This is our CalLight model. This feeds information into those neighboring subbasins outside of our Merced area. So we use CalLight to run those 100 years of hydrology for all those climate scenarios, to be able to get reservoir operations, stream flows that can be used for the groundwater model for these other subbasins. But another important component that comes out of this model is delta conditions. One of the triggers for doing FloodMAR is if the delta is in excess conditions. So we can use this CalLight model to see when the delta is in excess conditions and trigger our FloodMAR operations back here in the Merced Basin. Our DWR climate change group is the one that's been using and running this CalLight model. I say Wyatt Arnold and Roman Manley, especially. So then from there, we can go up to the watersheds now. So we use a SAC SMA model to model the upper watersheds that provides information into the CalLIGHT model and into the groundwater model. So this is also from the DWR climate change group. Wyatt and Romain have also been using this model. So this models the upper watersheds and feeds into the CalLIGHT model. So now we will zoom into our watershed and take a look at the models we're using specifically within our watershed. So again, we've got the SAC SMA model that does the rainfall runoff in the Merced upper watershed. That runoff then goes into our reservoir operations model. We have a ResSim model that we have borrowed from Merced Irrigation District. They have a suite of models that they've set up on their own that they've graciously let us borrow. That's part of their MID H2O program. So we've taken some of those models and made some augments and some changes to be able to use for this study. So this model will run the reservoir operations year-round, flood operations, irrigation operations, minimum stream flow requirements. All those operations are built into this model. And then with the FloodMAR scenarios, any FloodMAR operations. We'll talk a little bit about that later in our level 2, where we go to reoperate the reservoir. That'll be all part of this modeling. Inside of this study area, we do have a number of creeks as well. So we have another rainfall runoff model, an HEC HMS model, was also provided by MID H2O. This models all these creeks and a couple of the kind of simple flood control reservoirs on these creeks. And we do use water from these creeks as a source of FloodMAR water as well. This model is being run by our MBK consultants. So then all that information can then go down into our groundwater model. We had the information from these neighboring subbasins from the CalLIGHT, and then everything that's happening in here can come from our reservoir operations model, our HMS model, and we can get that surface water, groundwater interaction between all these models. And that gets us through our baseline modeling. Now to do FloodMAR, there's one more model that kind of comes in between here, and that's our recharge optimization model. In this case, it's GRAT. Which stands for Groundwater Recharge Assessment Tool. This model is developed by Earth Genome and Sustainable Conservation. I'm going to get into a little more specifics about what this model does here. So zooming a little further. As we get FloodMAR wafer, so water available for recharge from the ResSim models and the HMS models, we need to figure out where to put that water through the agricultural land using the Merced Irrigation District's conveyance network. We need to know how much water we can place there, how long can we flood these agricultural fields, when do we need to stop flooding them, let them do dry down. So that's what this recharge optimization model does. It takes a lot of information. It takes the wafer information. There's a lot of information that goes into this GRAT tool that I'm going to gloss over real quickly, but it takes information like the crop types, the soil types, agricultural practices, biological functions of all the different crops, and all this information goes in this tool to figure out essentially where are all the best recharge sites, how long can they be recharged, how much, the timing, all that information. So as the wafer is available from our other models, it goes through this GRAT model. The GRAT model can then tell us on a field by field basis, where all that wafer can go for recharge purposes. If not all of it can be recharged, it could tell us how much would end up being unused. That would either need to stay either in the river or stay back in the creeks as unused wafer. And then information from this model would then go into our groundwater model. The recharge on these fields is aggregated up to the cells of our groundwater model, and then that's applied as actual recharge applied in the groundwater model. So one last set of models is our flood models. It's FloodMAR. One of the benefits we hope from FloodMAR is flood risk reduction. So as we get information out of our reservoir operations and rainfall runoff models, we've done our FloodMAR recharge, whatever unused water that went for recharge that goes back to the streams, we get all the information, and then that all is input into our stream flow models. So here we have two HEC RAS models. These are also all from MID H2O. So we get the stream flows that run through these models, and then from there it feeds into a flood damage HEC FIA model, so we can calculate actual damages by event. We look at the specific flood events and we can calculate flood event damages. So that was a very quick overview of what all of our models are and how they'll integrate together. Some issues that we've been coming up across as far as integrating all these models. As you can imagine, trying to integrate 9 different models would have a lot of issues. Some things are like file formats. Some of these models have different ways of input, output, text, spreadsheets, DSS. We've had to develop scripts to move information back and forth between formats. Time steps, each of these models runs on a different time step. Some are as fine-tuned as hourly, some are more coarse at monthly. Run times, this gets into kind of our modeling sequencing. Some models run in hours, other takes days. So we need to kind of schedule and be aware of how long it's going to take to run models as we get through the sequencing from one model to the next. The model sequencing and iterations, like I said, just kind of planning all that out can be a little bit of a chore. Quality control, checking the results of 9 different models. There's a lot of quality control that goes into this, a lot of review. And I think our biggest issue, and this is a little bit of what Karandev will touch on, is the amount of data that's generated and the analysis of those results and metrics. With 9 models and 30 climate scenarios and 9 FLEDMAR scenarios, we are generating just terabytes of data. And it's a lot of data to sift through. So we're really trying to go through all that data, find what's meaningful, find the meaningful results and metrics, and process those in a way that people can read and understand what's going on. And I think Karandev has been doing a real great job with that, and he's going to show some of that we've done so far, just right now, actually. So I will hand it over to Karandev to take over.
Thank you, David. Perfect. All right, well, thank you for doing a wonderful job of setting us up for this next half of the presentation. So as we go through this segment, I want you to think of this sort of a 2-part segment. The first half will focus on kind of take a deeper dive into the results, how the results get communicated across the integrated toolset that David just explained. And then we'll just take a step back and just look across all these models in context of the 3 sectors that David outlined: flood risk, water supply, and ecosystem management, and see how the results track across those 3 sectors as we implement different levels of FLEDMAR project. So let's start with a deeper dive first. So what can we do now? That is level 1. And what can we do using the existing infrastructure plus the excess flows that are available to us? And again, the excess flows definition takes into account making sure that all the downstream uses are being met, the riparian diversions, the minimum in-stream flow standards, and also taking a look at the delta and making sure we're only diverting flows when delta is in excess conditions. So what you'll see with the results is the canal network ends up providing a substantial temporary storage space for recharge. So it's a critical component of doing recharge. But as we expand to do on-farm recharge, it does expand our opportunities for recharge as well as the amount of volume that can be recharged. And lastly, that the groundwater does not stay confined to its primary recharge basin. So the bar graphs I have over here show you the average annual applied recharge. So with the canal only scenario, we get around 17,000 acre feet per year on average. Now, when we expand to the on-farm recharge within the Merced watershed, that number increases to 43,000 acre feet per year on average. That's more than double. Now, in terms of where we can park that water for recharge, there are 3 possible places in the Merced watershed. First being the conveyance network, the second, the on-farm recharge, the agricultural fields that are available and kind of decided upon through the GRAT tool, as David mentioned, and lastly, the recharge basins. Now, for the canal-only scenario, 100% of recharge is done through the canal network, and that is by design because we limited our recharge just to that. Now, once we do expand to on-farm, we find that it's a roughly 50-50 split where half the water gets recharged through the canal network, the other half through the on-farm recharge, and we have 1% of the water that gets recharged through the recharge basins. This number is small just because under existing conditions, there are very limited recharge basins that are existing in the basin. So there's not a whole lot of water that can get recharged through recharge basins. Now, once the water is recharged, the next question is what happens to that water, the fate of the recharged water. Now, the three possible outcomes with that. First is the water gets retained in the primary recharge basin. Second, the water leaves the primary recharge basin into the adjacent sub-basin, but still stays within the groundwater system. And the third option is the water goes back into the stream system. What we find with our studies is roughly about a third of the water that's recharged stays within the primary recharge basin, and about 50% of the water flows out into the adjacent subbasin. So together, about 85% of the water stays within the groundwater system, and the remaining 15% or so goes back into the stream system. Now, with the amount of water that's being retained in the primary recharge basin, it's on a lower end just because the way the model was set up. So we assume pre-sigma conditions. And what I mean by that is as we are recharging the Merced subbasin and bringing it to some sustainability levels, the adjacent subbasins are still operating under the pre-sigma conditions. So, which is why we think there's a higher loss rate to the adjacent subbasins. We are running a sensitivity run just to kind of quantify that impact, but I don't have the numbers to share with you today. So now let's take a deeper look at the canal plus the on-farm scenario, just to see how the results kind of get communicated across different tools. The very first question that we start off with is how much water is physically available to do recharge? And what you'll see is about 2/3 of the water that's available for recharge comes from the Merced River system, and about a third comes from the local creeks. Now, with the major river systems like Merced River, they do provide a substantial volume of water, but the supply is intermittent. Whereas the local creeks, they provide a smaller quantity of water, but the supply is more reliable and continuous over that 100-year simulation period that we're looking at. So in the table below, I have listed the cumulative volumes of water that are available for recharge from different stream sources. The 100-year cumulative volume is around 4.7 million acre feet. Roughly 68% of that comes from the Merced River system, and the remaining 32% comes from the local sources, be it the smaller creeks or the runoff from the foothills. And if you divide 4.7 million acre feet by 100, you get that on average about 47,000 acre feet is available for recharge, and a maximum single year of water is around 300,000 acre feet. That's about 6 times the annual average there. In this graph, I'm showing the amount of water that's available for recharge across the 100 years of the simulation period that we have. In blue and outlined in black are the flows that are available, the volumes that are available from the Merced River system, and the other colors represents the local sources of water. And as you can see, when the water is available, there's a huge quantity of water that's available from Merced River, but it's not available every single year. Whereas the other shades do show up consistently across a 100-year period. It's a smaller quantity, but more reliable supply source. Over the 100 years, the purple line in the background is tracking the cumulative WAFER, which stands for water available for recharge, and that adds up to that 4.7 million acre feet over the 100 years. So now we know how much is available. Now the question is when it's available, the timing of that. Just like the intra-annual variability, we see a similar trend in the daily variability of flows, where the major stream systems like the Merced River, they do provide huge quantities of water, but they're concentrated over smaller periods of time, ranging from a few days to a week. And the local sources provide a more continuous supply of water. Now that presents a logistical challenge in terms of managing these excess flows and kind of being able to line that up with the available capacity to move that water to do recharge through the conveyance network or through the on-farm. And what we find is by combining FloodMAR with reservoir reoperation, we're able to manage that variability better. We're able to manage the timing, the release of those excess flows with the diversion capacity being available to move those flows to the agricultural fields. And based on the results, what we find is the yield from a FloodMAR project goes up by 1.5 to 2 times as a result of kind of coupling the FloodMAR with reservoir reoperation. Now, we have looked at how much is available, when it's available. The question is, can we use it all? And the answer is almost all of it. So what we see is on average, about 10% of the available water is left unused. And this is primarily for 2 reasons. Either we get too much water over a concentrated period of time so that we are limited by the delivery capacity to move that water, or the water shows up too late in the season and we're limited by the amount of land that's available to apply that water, or by the canal the leftover canal conveyance capacity to take in that extra water to do recharge. So typically the agricultural activity starts to pick up late February, early March, and that's when we see the second reason kind of becoming more prominent, that the water showing up in that part of the season, we have limited resources to put that water. Now, in this bar graph, I'm showing the same, the amount of water that's available for recharge. I've just changed the colors. Blue represents the amount of available recharge that is applied. The red is the unused wafer. So on average, we have 47,000 acre feet available per year, 43,000 acre feet per year gets applied, and the unused is around 4,000 acre feet per year, such that over the 100-year period, the cumulative available is 4.7, the cumulative applied is 4.3 million acre feet. And one of the things I wanted to kind of point on this graph is the relationship between unused and used wafer. There are years when there's a lot of quantity, there's a huge quantity of water available, and we end up using a lot, most of the water. And then there are years when there's not a whole lot of water available, and most of the water goes unused. And that kind of goes back to when we think through the FloodMAR projects, it's not just the volume, but the timing also matters in context of when the water becomes available to do recharge. Now, an additional consideration with recharge is which fields are available to do the recharge. And David did a nice job of kind of walking through the GRAC tool that's prepared by Sustainable Conservation and Earth Genome that goes through the different parameters to determine which fields are available to take water, how much water can they take, and based on that, we basically have a sense of the available agricultural land that's available to do on-farm recharge. And one of the criteria that we apply is we try and prioritize. So once we have a sense of the fields that are available to do recharge, we can then go ahead and do ranking within those fields to make sure we prioritize the best fields. And the definition is fluid, and the way we define it is fields with good drainage, higher depth to groundwater, and outside of the cork clay layer, so they have more access to the groundwater aquifer within the Merced subbasin. So there's a higher chance of water being retained in the primary recharge basin. Now, additional criteria can be applied to start prioritizing certain fields, which is what we start to do with level 2 runs. And I'll get to that in a minute. So with level 2, we're kind of coupling the existing infrastructure with reservoir reoperation. And in addition to that, we start focusing on different management objectives. And one of the things we can start to do is start prioritizing fields that help improve the water supply reliability for disadvantaged community places within the Merced watershed, or concentrate recharge in the subsidence-prone regions of the basin. So, there's additional criteria that could be applied in addition to just, pure field selection based on the best access to do groundwater recharge. So now that we have a sense of, how much is available, how much gets used, where the water gets put, the next question is, where does the recharge water go? Right. So on this graph, we have the groundwater budget, where the inflows are in blue and the outflows are in gray. And the additional recharge that's done is shown in these yellow bars. And the blue line in the background is a cumulative change in groundwater storage. And the axis for this is over to the right there. We start at 0, And then we track the cumulative change in groundwater storage as a result of the effect of inflow and outflow into the groundwater aquifer system. The dashed line represents the baseline conditions. The solid blue line is the level 1. That is a scenario with FloodMAR. So over time, as we do recharge, we do see an improvement in the overall, or an improvement in the cumulative change in groundwater storage. So let's put some numbers to this slide here. So we started off with 47,000 acre feet being available on average. About 90% of that was applied. That's 43,000 acre feet per year. So that's those yellow bars in there. About a third of that water was retained in the primary recharge basin. That comes out to around 14,000 acre feet per year on average. And if you multiply 14,000 acre feet by 100, you get around 1.4 billion acre feet. So that's the improvement you see in the cumulative change in groundwater storage, where in the baseline, the cumulative change in groundwater storage was around 5 million acre feet. Now it reduces down to around 3.6 million acre feet. So now that we looked at the operations of a FloodMAR and how these results, the model inputs and outputs gets exchanged between different tools and how we arrive at the end result, I like for us to kind of switch into more of a high level overview to start tracking the results across the 3 categories that we listed: the flood risk, water supply, and ecosystem management. And the goal of the results that we select to highlight under these categories is to assess the public and private benefits that are associated with FloodMAR projects, namely flood risk reduction, improved water supply reliability, aquifer replenishment, ecosystem enhancement, and drought preparedness. Now, before I get into my next slide, we do have a poll for you. So, or if you can bring up the poll for our audience, please.
So everybody should be able to see the poll. There we go. So just a few more seconds to let us know which water management sector you most closely align with: flood, water supply, ecosystem. All right, I'm gonna end the poll, and here you go.
Perfect, thank you. Well, it looks like we have a good representation of the water supply sector, but we still have some representation from flood and ecosystem. So we'll definitely be covering all 3 categories. So keep an eye out for results in each category and see how FloodMAR tracks across those 3. All right, so as we present well, let's get into key findings just briefly. So what we find through our results is FloodMAR provides multi-sector resilience. We do see fewer, it reduces the flood risk by lowering the peak flow magnitude and by reducing the frequency of high flow events. We do see an improvement in groundwater conditions, which ends up then improving the water supply reliability by recharging groundwater basin and reducing the long-term overdraft rate. And lastly, the ecosystem category, we're still kind of working our way through that, but we find is by skimming off the high flows off of the stream system, we see a marginal effect on the in-stream habitat availability, but by recharging those flows and therefore improving groundwater levels, we do see a more reliable habitat being provided for the groundwater dependent ecosystems. Now, as we combine FloodMAR with reservoir reoperation, we find there are substantial benefits to all 3 sectors. We observe a significant decline in peak flow magnitude and high flow events. We observe a substantial increase in the amount of water available for recharge, which eventually helps improve the long-term water supply reliability. And also any decline in surface water deliveries as a result of reoperating the reservoir is more than offset by or mitigated by the additional recharge that's done through the FloodMAR project. So overall, and then lastly, with the reservoir reoperation, it ends up providing those additional opportunities to further improve ecosystem functions. So one of the scenarios I'll be discussing with level 2 is called eco-feromar, and the word eco kind of represents that we're trying to maximize the ecosystem benefits, and we do so by establishing a dedicated shorebird habitat in month of March, by creating additional spawning and rearing habitat for fish by inundating floodplains, or by conducting these controlled spring pulse releases to help with fish out migration, all the while minimizing the impact on water supply. So let's take a look at the results and put some numbers behind these key findings. So what you'll find as we go through the results, I'll be referring to this table. So I wanted us to kind of get oriented to this table. So we're tracking results across 3 categories: flood risk, water supply, and ecosystem management. And as David said, it's a work in progress. So, numbers can change, and we're just sharing as we are kind of processing the results. The first set of slides are going to focus on the current climate conditions. And as you look through the numbers, obviously the numbers are good to look at, but I want you to kind of pay attention to the red and green, and they represents the performance indicators. If you see a red, that's a decline in performance, meaning there could be an increase in flood risk, or reduction in water supply reliability, or some sort of reduction in the habitat that's available to different ecosystem species. And then and green would be the improvement. So reduction in flood risk, improvement in water supply reliability, or improvement in the habitat conditions. So let's start with the first category, flood risk. So for the flood risk, we're tracking Merced River flow at Crocker-Hoffman, which is a relatively upstream location along the Merced River. And this is just downstream of the diversion point for the LunchMAR project. And what we're tracking are 2 things at this location: the number of flood spill events defined as flows greater than 8,000 CFS, and the 100-year simulated peak flow magnitude based on our studies. And just as a reference point, in the lower half of the Merced River, the channel capacity is around 6,000 CFS. Now, under the flood risk category, what we find is the system is adequately designed to handle flood flows under current conditions. There are no events above 8,000 CFS, and the peak flow magnitude is seen for the 1956 simulated event is around 6,000 CFS. And with level 1, we don't really end up making any changes to those results. So under current conditions, there's very limited flood risk benefit for level 1. For the water supply category, we're tracking the groundwater storage, the surface water storage at Lake McClure at the end of the irrigation season, which is defined as October 31st. We're tracking the groundwater conditions in the Merced subbasin by looking at the average annual basin-wide change in groundwater storage, or you can think of that as the long-term overdraft rate. And lastly, we're tracking the agricultural applied water demand that is met by pumping groundwater or through surface water deliveries. So for that category, we find in terms of the reservoir storage or the amount of water that's available to the agriculture users through surface water deliveries or groundwater pumping doesn't really change with level 1. And that's because we're not changing the reservoir operations. The allocations remain intact, so there is no effect on that end. Now, in terms of the long-term groundwater overdraft rate, as David mentioned, over the 100-year period, the average annual is around 50,000 acre-feet per year. That rate reduces to around 36,000 acre-feet per year. That's a reduction of 14,000 acre-feet per year on average. And if you recall, that was the amount of water that was retained in the primary recharge basin. And the top row, I'm just tracking the amount of water that's available to do recharge. And that is that the amount of water that gets applied to do recharge. And that is that 43,000 acre-feet per year. Moving on to the last category for ecosystem, we're tracking habitat availability for the groundwater dependent ecosystem, and then for the 2 managed species in the Merced River system, the Chinook salmon and then steelhead. For the groundwater dependent ecosystems, we're tracking the depth to groundwater. So according to the Merced Groundwater Sustainability Plan, the maximum rooting depth of a groundwater dependent ecosystem is around 30 feet. And we're tracking the number of months with groundwater levels at or above the 30-foot depth in regions that are dominated by groundwater dependent ecosystem. For the 2 managed species, we're tracking the availability of in-channel spawning habitat along the Merced River. So there are a few caveats. So let's go with, so why only the in-channel habitat? That is because under current conditions, the habitat along the overbank areas lacks the necessary conditions to support fish through different life stages. So it's not useful until some restoration is done. So which is why we're focused on in-channel. And why the spawning life stage? And out of the 3 life stages, we do look at results all 3. We're just focused on presenting the results for spawning just because it's considered the most critical life stage for the fish. Now, how are we tracking it? We're looking at the weighted usable area and flow relationships that are included in the Merced Irrigation District's FERC relicensing documents. So these relationships are provided for 3 sub-reaches along the river for the 3 life stages: fry, juvenile, and spawning. And the one we're focused on is spawning, which is in green. So if you can just isolate the green curves on this graphic here. And in terms of the shape of the curve, so if you look, the flows are only evaluated through 1200 CFS. That is because based on some of the analysis we did, we found that flows exceeding 1200 CFS, that's when the water starts to get into the overbank areas. So we're only looking at the component of the curves between 0 and 1200 CFS. And the shape resembles an inverted U. And that's because that's kind of more specific to the Merced River system, such that it's a highly channelized system. It behaves more like a canal and less like a traditional river, which means too much flow results in deep, fast moving flow, or too little flow results in shallow, slow moving flow, and both of which are not ideal for fish. So the sweet spot based on these WUA relationships within the in-channel habitat is around 400 CFS. So what we're tracking specifically is the percentage of the maximum weighted usable area that's available for spawning. That's a lot, and we can get back to it in the questions if there are any further questions on this. So in terms of the ecosystem management, with groundwater dependent ecosystems, the percentage of months with depth to groundwater less than 30 feet, we'd see some improvement there from 77% of the months being in that category to now 82% of the months. With the in-channel spawning habitat, we don't see a whole lot of difference in the habitat available before and after we do the LunchMAR project. And again, with the in-channel spawning, I do want to point out that we are not running the temperature modeling. That's another component to all this, and it could have a significant impact on the health of the fish and the habitat availability. So that's sort of a blind eye for at least the analysis that we're doing. So obviously more could be done to assess these impacts better. Now with level 2, we're taking that recharge and coupling it with reservoir reoperation. And as I said, we explore a range of management objectives. One of those is called EcoFeromar, where we focus on managing the reservoir for ecosystem benefits. The other end of it is the recharge pool MAR, which focuses on kind of maximizing the water supply benefits. And we can come back to this if there are more questions, but that's kind of general gist of it. Now, if you look at the level 2 results, I like you to kind of focus on first the kind of the long-term groundwater overdraft. So it was 50,000 acre feet. With level 1, we reduced it down to 36. With level 2, we're able to reduce it down to 20,000 acre feet per year. So that's about a 60% reduction in the long-term groundwater overdraft rate. And also, as we're able to align the reservoir reoperation with the recharge operations, we're able to benefit from increased volumes of water being available to do recharge. So the applied water volume was around 43,000 acre feet per year. It goes to 54 to somewhere between 80,000 acre feet per year on average with the level 2 scenarios. And we're still working through the results, which is why you see a lot of TBDs in other categories. Now, with climate, I just want to show you one brief results before we conclude here. So David kind of described earlier, it's the 100-year hydrology. We're looking at 30 climate scenarios. We for the next slide, I'll just focus on two specific climate scenarios. One is current conditions, which is what we have been looking at. No change in temperature, no change in precipitation. And I'll be comparing it to a future climate, which is 3 degrees Celsius change in temperature and 10% increase in precipitation. And this kind of falls within the range of most likely scenarios by 2070. And for most part, I like to kind of focus on the flood risk category there, where under current conditions, the system is adequately designed to handle those flood flows. With climate change, we see the peak flow increasing from 6,000 CFS to 42,000 CFS. With level 1, we're able to manage some, but it's not a huge improvement. But as with level 2, when we couple those reservoir reoperations, we do see a significant improvement or reduction in the peak flow magnitude, going from 42,000 CFS down to 15 to ranging from 6 to 15,000 CFS, depending upon how you set up the reservoir reoperation. And another thing I just wanted to point out is we see an improvement in the long-term overdraft rate, despite seeing an increase or an uptick in the groundwater pumping, which is kind of, as we do reservoir reoperation, we end up changing the storage conditions, we end up impacting the allocations, and eventually affects the amount of surface water that's delivered to the agricultural users. So we do see there's some reduction in the amount of surface water deliveries to the users, and that reduction in surface water deliveries gets compensated by additional groundwater pumping. But even though that is happening, we still see that on the net, there's still improvement in the groundwater conditions and a significant reduction in the long-term groundwater overdraft rate. So that concludes our presentation. There, obviously it's not a complete analysis. We're missing water quality, temperature, subsidence. There are a few modeling assumptions I can get into if there are specific questions on this. But overall, this is the results summary that we have for level 1, which is existing infrastructure plus excess flows, and level 2, which is reservoir reoperation plus recharge. And as David mentioned, I do want to acknowledge there's a lot of folks behind this analysis, and you only see the 2 of us kind of doing the presentations. There's a lot of brain power and a lot of specialization that went into this analysis. And I see some of those folks are joining us on the call here today. So, if there are any specific questions, I'm most likely going to throw your way, so be prepared for that. So with that, we wrap up our presentation and we're open for questions.
Thanks so much, David and Karandev. There's about a handful of questions in the chat, but I will also invite people to turn on their cameras and unmute themselves if they'd like to ask a question. But I will just start in the order that they were received. And if we don't get to your question, we'll capture it in the meeting notes and ask David and Karandev to do a little homework in responding to questions. So first question is from Richard McCann. Of the 15% stream return, is that return immediate or is it returned on a delayed basis?
What we find is, so the water shows up in the Merced River system, and a portion of the water shows up in the San Joaquin River system, which runs along the western boundary of the Merced subbasin there. And with respect to the Merced River, it's an immediate return, same month to a few months lag. With the San Joaquin River system, it's we do observe some delays, even the water showing up even in the following season as well. So depending upon the location, it varies, but we do see both.
Yeah, this is Richard McCann. Can I just quickly follow up on that? Which is, I was thinking when I said immediate, I really mean immediate. Whereas a delay of a month or 2 months may actually give you flood control benefits. That's why I was asking that question, right? Because if you can spread out the release, that relieves your flood spike.
And yeah, so one of the things that's hard to answer that question in terms of is this really immediate is because the resolutions, the groundwater model is a monthly time step, the recharge operations are daily time steps. So we do see instances of water showing back in the system in the same month, but how immediate beyond that month is hard to answer. But there's obviously, there are some, that we also observe a delay by a month or 2, or even by an entire year. So there are some benefits there as well.
Thank you. We've got a question from Mike Antos. Can you go over how the water available for replenishment comes after in-stream and riparian need for water?
So, sorry, go for it.
I can talk about the in-stream part if you want to talk about the riparian, but you go ahead.
Sure. I think so with our reservoir, that's why there's a huge modeling tool set. The RESM model does represent the riparian demand, the minimum in-stream flow requirements, and those are all accounted for. So before, we've written up code to make sure that we provide enough water to meet the allocated surface water deliveries, the riparian uses that exist along the Merced River, as well as the riparian uses that exist along the local creeks, and the minimum in-stream flow requirements along the Merced River. And then the CalLITE model allows us to look at the delta, even though, these models are, they're connected, but, it gives us some sense of how the delta is behaving, whether it's excess balance or excess with restriction, and we try to limit our diversions when delta is in excess. So all that is kind of baked into the RESM model for the Merced watershed, and CalLITE provides us the input for the delta. Dave, do you want to add something?
No, I think you got it.
Thank you. Question from Peter Nico. For the level 2, does the groundwater moving out of basin similar to level 1, so the 30%, 50% split, or does even more water move out of the basin?
Gonna go for it.
I think you got the groundwater results.
Okay. All right, well, the results were just off the press just last week, and we're kind of observing a similar trend, and that's why they didn't make it into presentation here. But it's about a third of the water stays in the primary recharge basin, about half leaves, and about 15% kind of goes back in the stream system. And again, that ties to the sigma assumptions, as we're exploring the sensitivity of the results of those.
So in the sensitivity analysis, are you changing conditions in the adjacent basins to see how that changes the percent that's leaving?
David, I think you're the best candidate.
Yeah, we're trying to figure out a way to assume that the other basins have achieved sustainability, basically that the groundwater levels are not dropping. We haven't quite figured out, it'll be through the groundwater model. We haven't quite figured out how exactly we want to approach it. But that's the general idea, is to kind of maintain all the neighboring subbasins.
Yeah, I'm just going to jump in. I mean, you said it a bunch of times that you're working on it, but obviously it makes almost a factor of 3 difference in the impact on the existing basin, right? So it's a huge lever on the benefits.
Probably, yeah. I don't want to say what exactly is going to happen until we see, but yeah, it will probably be a pretty huge lever, like you said.
I just wanted to add to it. One of the reasons these sigma conditions were not included, and David, correct me if I'm kind of misstating anything here, is when the study started about 2.5, 3 years ago. At that time, the plans were still coming in, so we didn't want to make any assumptions as to how the basins would get into sustainability or achieve that sustainability, which is why we stuck with the pre-sigma assumption in our tool set. Now that those plans are out, so we're kind of doing our best to make sure that, if they find a reasonable way to kind of represent that through the sensitivity analysis. And so just wanted to give some context why that assumption was not there in the first place.
If I can add to that, Peter, the assumption of sustainability doesn't necessarily mean that the groundwater gradient reverses. So there still may be flows out of the basin. As you
definitely know, the sustainability isn't actually the important bit. It's really understanding all the flows between the different basins, depending on what the different gradients are. But either way, there's kind of right now in the accounting, a large part of the water just kind of disappears and isn't showing up on the red or green summary charts at the end. But obviously in real life, it's going someplace. It's showing up as red or green on somebody's summary chart. So that was the idea, that it's still out there somehow to be put into somebody's accounting. Yeah.
Exactly.
Yeah, somebody's going to benefit from it.
Right.
Well, we've got about 5 more questions. So David and Karandev, we'll give you some homework. We'll share what those questions are and ask you to respond to them. I will include in the LunchMAR summary, but I would invite everybody at this time to give David and Karandev a virtual round of applause, thumbs up, or raise your hand to give them a high five. And I thank everybody for participating today. We're on LunchMAR 13, so happy over 1 year anniversary. And we've got one last question for you if your presentations were relevant to the work that you do. And I invite anyone to put any announcements that they have in the chat. I know there's a handful of things that I'm going to rattle off really quickly. We've got network initiative meetings in June. So if you didn't receive an email about those meetings, let me know. We're planning another network workshop in late August, early September. We're also planning our next FloodMAR public forum for early November. If you'd like to be on the planning committee for the public forum, just shoot me an email or type it in chat. There is a deadline for abstracts on June 14th for ISMAR in Long Beach in April of 2022. Hopefully Adam will add a link to the call for abstracts in the chat. And lastly, on June 8th, there is a DWR hosted webinar on AEM. So if you are interested, let me know, shoot me an email, and I can send you the meeting information. But thanks again, everybody. Thanks again, David and Karandev. Wonderful presentations. We'll see you next month. Sorry, David and Karandev, you guys are going to have a little bit of homework. But it's, they all look like questions that you guys will be able to get to pretty easily.
Are you going to collect them and send them to us?
Yeah, Danica normally collects and sends out the questions.
So if I received a direct message, then I guess I should save it for myself, right?
Yeah, Danica, you can only see the everyone messages, right?
Sorry, I was on mute. Yeah, I can't see the everyone. I mean, I can't see the direct messages. I can only see the everyone.
Sounds good. So I'm just going to copy that message and send it to you so you can compile with other questions.
Okay, it was a question. Okay.
Yes. Mm-hmm.
So this Kamyar, so it might be good to start building an FAQ, and that way we'll post it and we can direct people there, and especially as you make more presentations, it'd be nice to share the back and forth from prior engagements.
Yeah. Great presentation, you guys. Really nice to see the current version.
Keeps getting better.
It does.
Yeah.
You need another hour though.
Yes. That's why I keep telling you. So a lot of these slides are just trust us and let's just move to the numbers. We're trying.
A brunchmar. That's the 2-hour version.
Sounds like a plan.
Well, don't you guys fret, because we're at least, dedicating half a day for Merced results for the public forum. So
We'll be able to fill it.
we dive deep.
Yeah. All right.
That was great. Thank you.
I'll see you guys.
Great slides and presentation.
Yeah.
Thank you.
Everyone.
Thanks all.
Bye-bye.